Batteries in a circuit are modeled with the following diagram, a plus and minus in a circle. Batteries generate a potential difference between their negative side and their positive side. A 9-volt battery will create a 9-volt potential difference between this point and this point. So this point will have 9 extra volts, or a 9-volt rise, compared to this point. Current flows from areas of high potential to low potential. But because of the way batteries work, they could output, theoretically, an unlimited or very high amount of current. The reason current doesn't travel infinitely fast is because there are particles inside of wires that charged particles tend to bounce against. This means that to keep the charged particles moving throughout the circuit, the battery needs to use its energy. Remember Newton's law: an object in motion will stay in motion unless acted upon by an outside force. And incidentally, in a superconducting wire, you can actually have a particle moving around for what is basically an indefinite period of time without any force needing to be applied to it. But in a normal circuit with resistive wires, in order for particles to keep moving, they need the energy given to them by a battery. Normal wires have extremely low resistance, so even small batteries will cause current to travel through wires extremely quickly and end up burning out the wires or even melting them. Resistors are stretches of wire or some other device that provides a lot more resistance to a particle that's trying to travel through them. That is, it takes more energy for a particle to push through a resistor than it does for it to push through a normal wire. The 9 volts of a battery in this circuit are used to force charged particles through the resistor. But the battery can only provide so much energy to particles, and so those particles will only be able to travel so fast through a resistor and all the resistance that it provides. A resistor's resistance, which is measured in units of ohms, often called R, is equal to the ratio between voltage and current. What does this mean? Resistance basically says if your particles have this much energy, they can travel through with this much current. We can rewrite this equation as I equals V over R. This says that the higher the resistance, the lower the current will be through the resistor given a certain voltage. So resistance basically describes the maximum amount of current that can travel through a resistor given the amount of voltage you're able to provide to that resistor. For example, this resistor is experiencing the 9 volts that this battery is providing. All those 9 volts are to be used up across this resistor. So if we want to find out the current that will be able to go through this resistor, we can plug in I equals 9 volts over 10 ohms. Volts over ohms equals units of amps. Amps is the units of current, and 9 divided by 10 is equal to 0.9 amps. The final way that this equation can be written is in the form V equals IR, which basically says that if you see more current going through a resistor, there must be more voltage across that resistor. This is the classic statement of Ohm's law. Ohm's law is not a real law. Ohm's law is basically a mathematical tautology that describes a ratio. This is really just another way to write this ratio, which describes if you look at a thing and you ask, given a certain voltage, how much current can pass through it, you are looking at the resistance of that thing. But Ohm's law is basically an expression of this ratio, and R is defined as this ratio. Throughout this course, I will often describe a resistor without the little zigzaggy thing. I'm just going to write down its resistance value in the middle of the circuit. In circuit analysis, it is a useful mathematical tool to talk about something called a voltage drop. A voltage drop is, in some sense, how much of the voltage of an electron, of a charged particle, gets used up when you travel over something like a resistor. Now let us say there are 2 resistors in this circuit. We know the particles don't slow down upon going through a resistor. In fact, the current through this entire circuit is the same at all points in the circuit. But energy is being used by the resistor. The particles bouncing around are being converted into heat. So we can describe the relative effect that a resistor has on the speed or on the current of particles in a circuit, or in a sense how much energy or how much voltage it uses, with something called a voltage drop. These two 5 ohm resistors have roughly the same effect on the speed of particles in the circuit. Their effects add together. So we can say that they equally divide the voltage among themselves. So each resistor experiences a 4.5 volt drop. Any particle passing through this circuit has to pass through both resistors and imparts energy to both resistors. Because it is traveling at the same speed through the entire circuit, it imparts the same amount of energy to both resistors, so they both get 4.5 volts worth of the energy that the battery provides. And all of the particles in the circuit move slower because of the effect of the two resistors combined. Once a particle gains its 9 volts from the battery, it can travel on any path through the circuit. It could travel through this 10 ohm resistor, or it could travel through this 10 ohm resistor. Because it has 9 volts worth of energy, it'll travel at the same speed through either resistor. This is why we say that there is a 9 volt drop across each of these resistors, as opposed to a 4.5 volt drop like over here. On any path through a circuit, a particle must use up its 9 volts. For example, a particle could use up its 9 volts traveling through this 5 ohm resistor, then this 10 ohm resistor, or through this 5 ohm resistor and then this 10 ohm resistor. But when circuits start looking complicated, it gets harder to determine just by inspection how much of the energy of a battery an electron will provide to any given resistor. How much energy would go to this 10 ohm resistor? How much energy would go to this 5 ohm resistor? This is where the concept of voltage drops becomes super helpful. As we do analysis, we can determine what the voltage drops across various different resistors in a circuit are. Let me talk a little bit about notation. We won't be able to do analysis just yet, but this plus and minus represents something about the relativeness of voltage. I happen to know with my secret analysis powers that there's a 4.5 volt drop across this 10 ohm resistor. When you see a positive and a negative terminal and a voltage in between them, the voltage means that the positive terminal is 4.5 volts higher than the negative terminal. That means that if a particle were to travel from the positive to the negative terminal, it would be using up 4.5 volts worth of energy. Now we know that there's also a 4.5 volt drop across this 10 ohm resistor because the two resistors are in parallel. But what if, when we were analyzing this circuit, for some reason we decided to write our unknown voltage with these two terminals? What would we find out this number for V would be? We could write negative 4.5 volts. This means, weirdly enough, that the positive terminal is negative 4.5 volts higher than the negative terminal. Or, more accurately, the positive terminal is 4.5 volts lower than the negative terminal. That makes sense, because on this side, this spot is 4.5 volts lower than this spot. So it should be that this positive terminal should be 4.5 volts lower than the negative terminal. So that's just how to interpret it. If you see a negative sign in front of the voltage between two terminals, that means that the positive terminal is lower than the negative terminal, as opposed to higher than the negative terminal by this amount. You may have noticed that we've only been talking about voltages in terms of relative numbers so far. This point is 4.5 volts lower than this point. This point is 4.5 volts higher than this point. This point is 9 volts higher than this point. That's because particles don't really have an absolute voltage. Voltage is just a relative thing representing how much force, in a sense, was used to push, how much energy that a particle has gained when traveling, or lost when traveling between 2 points. However, we can talk about absolute voltages in a pretend way if we describe some 0 point. The 0 point is called the ground. We can put down a ground in any circuit, and that point will be called the point of 0 volts. You can then mark other locations of a circuit with voltages based on the voltage drops and rises. For example, if this point is 0 volts, and this point is 4.5 volts higher than this point, then this point must be 4.5 volts. Again, since this point is 4.5 volts higher than this point must be 9 volts compared to the ground. That makes sense because this point is 9 volts higher than this point, so this point must also be 9 volts. This concludes our lecture on Ohm's law and voltage.